Right now, you are moving at over 1,600 kilometers per hour, and you cannot feel it. That speed is baked into every atom of your body, every building around you, every ocean on this planet. And for the next few minutes, we're going to find out exactly what happens when it stops. 6 seconds. That's all we're giving it. Not a permanent stop, not a slow crawl to zero over millions of years, just 6 seconds of nothing. And here's the thing, most videos won't tell you. 6 seconds sounds almost gentle. A sneeze takes longer, but the physics of what happens in those 6 seconds is so specific, so measurable, and so dependent on exactly where you're standing on this planet that two people could experience this event completely differently. One walks away confused, the other doesn't walk away at all. We're going to go through this in order. The deceleration force, the atmosphere, the energy math, what happens to your GPS, what happens to satellites, and one detail about the direction of down that almost nobody talks about. And I'll save the strangest one for last because it's the one that makes you realize this isn't just a thought experiment. It's already happening, just slowly. Here's what most people picture when they imagine Earth stopping. Everything flies off the surface. Giant storms, total chaos. The end. And, sure, broadly, that's in the right neighborhood. But the detail that changes everything is this. The deceleration force is not equal everywhere. A point along the equator moves at approximately 1,037 miles per hour, or about 1,668 kilometers per hour. That speed decreases with distance from the equator, and at the poles, it's essentially zero. So if the planet stops, someone standing in Quito, Ecuador, or Singapore gets hit with the full force of that stop. Someone in northern Canada or Antarctica, they feel almost nothing at the moment of deceleration itself. Your survival in this scenario is not about luck. It is entirely about your zip code. Now let's put a real number on what that deceleration actually feels like at the equator. We're spreading this stop across 6 seconds, not an instant. That works out to a deceleration of roughly 77 meters per second squared, about 7.9 times the force of gravity, sustained for 6 full seconds. Fighter pilots are trained to handle G-forces, and they typically black out somewhere between 5 and 6 G in just a few seconds. We're talking about nearly 8 G for 6. If you're standing anywhere near the equator, you don't stumble, you don't get thrown. You experience a force that would incapacitate or kill most people before the 6 seconds are even up. Survival chances increase dramatically near the poles, where rotational speed is lower at about 89.9 degrees latitude, roughly 7 miles from the poles. Someone might stumble forward at walking speed. That's the difference. Not a bunker, not preparation, latitude. So that's the body. Now let's talk about the air, because this is where the numbers get genuinely hard to believe. When the ground stops, the atmosphere doesn't get the memo. If Earth stops spinning, all the water, air, and structures on Earth would still be moving at speeds corresponding to their latitudes. At the equator, that means the air keeps rushing eastward at roughly 1,670 kilometers per hour, even as the surface underneath it goes still. The speed of sound at sea level is about 1,235 kilometers per hour. So the resulting wind isn't just catastrophic by any storm scale we have, it's supersonic. Mach 1.35 everywhere at once. There is no category on the Fujita scale, no classification on the Saphir-Simpson scale that describes what that is. Those scales top out at wind speeds that are less than half of this. The wind wouldn't just knock structures down. It would reduce them to fragments and accelerate those fragments into everything else. The planet's rotational kinetic energy is on the order of 2.1 times 10 to the 29th power joules. And if rotation stopped suddenly, the atmosphere wouldn't instantly stop with the surface. Those enormous stored motions would translate into extreme winds and reconfigured weather systems. And speaking of that energy number, 2.1 times 10 to the 29th joules, let's put that against something you can actually picture. The Hiroshima bomb released roughly 6.3 times 10 to the 13th joules of energy. Earth's rotational kinetic energy is approximately 3.4 quadrillion times that. 3.4 quadrillion Hiroshima bombs worth of energy, needing somewhere to go. Most videos just say cataclysmic. That's the actual multiple. Now here's where I want to correct something you've probably heard before because it comes up in almost every video on this topic, and it's wrong. People say that if Earth stopped spinning, satellites would fall out of the sky. They wouldn't. A satellite's orbit is governed by gravity and velocity, not by what the planet underneath it is doing. GPS satellites circle the Earth at an orbital radius of about 26,000 kilometers. Geostationary satellites sit even higher, and their orbits don't change just because the ground stopped rotating. What actually changes is their relationship to the ground. Geostationary was never a physical anchor. It was just a description of a satellite that matched a spinning planet's rotation rate. Stop the planet, and those satellites keep moving in their orbits. From the ground, they'd start visibly drifting across the sky, which is strange and disorienting, but they don't fall. What does break, though, is GPS. And the reason is oddly specific. GPS receivers must account for the motion of the receiver due to Earth's rotation during the time it takes a satellite's signal to reach it. This is called the Sagnac effect, and it amounts to up to 133 nanoseconds of correction at its maximum. Without Earth's rotation, the correction becomes irrelevant. But the problem is that GPS was built from the ground up, assuming that rotation exists. It doesn't just glitch. The whole timing infrastructure becomes structurally obsolete and would need to be re-engineered from scratch. Every navigation system, every precision instrument, every aircraft approach system that depends on GPS. Gone, not because the satellites fell, but because the math they were built on no longer applies. By the way, if you're finding this more interesting than you expected, drop a comment right now with where you live. I genuinely want to know whether you'd be in the supersonic wind zone or the just stumbles forward zone. And if you want to go deeper on how Earth's rotation already affects time, GPS, and the Coriolis effect in ways most people never learn about, I've got another video that goes exactly there. It's linked at the end. Now here's the one that almost nobody talks about. And this is the mega loop I opened at the start. The detail that proves this isn't purely hypothetical because a version of it has already happened. The massive earthquake that struck northeast Japan in 2011 shifted how the planet's mass was distributed, and a new analysis found that it accelerated Earth's spin, shortening the length of the 24-hour day by 1.8 microseconds, according to geophysicist Richard Gross at NASA's Jet Propulsion Laboratory. The calculations also show the quake shifted the position of Earth's figure axis, the axis about which Earth's mass is balanced, by about 17 centimeters. The scenario is similar to a figure skater drawing her arms inward during a spin to turn faster on the ice. Mass moved closer to the rotational axis, Earth sped up, the day got shorter, and we measured it. That's the same principle, conservation of angular momentum, that the entire what if Earth stopped thought experiment is built on. It's not theoretical physics. It's something NASA tracked to the microsecond after a single earthquake. Over billions of years, that process heads towards something called tidal locking, the same reason the moon always shows us the same face. That's real, it's ongoing, and it's completely different from a sudden 6-second stop. The gradual lunar process is natural and imperceptibly slow. A sudden stop is a thought experiment, not a trajectory we're on. I want to be clear about that because conflating the two makes both harder to understand. One last thing before we close, and this one is genuinely subtle. Earth's spin generates a slight outward pulling centrifugal effect that acts in opposition to gravity, and it's strongest at the equator where rotational speed is highest, causing a small reduction in apparent weight. If rotation ceased, that centrifugal force would vanish, causing a measurable increase in apparent weight across most of the globe. At the equator, a person would immediately feel approximately 0.3% to 0.4% heavier. But here's the stranger part. The direction of straight down would also shift. Right now, a plumb line doesn't point exactly toward the center of the Earth at most latitudes because the centrifugal effect pulls it slightly outward. Remove rotation, and that correction disappears. The direction of true vertical changes almost everywhere on the planet. Buildings, bridges, and instruments calibrated to the old vertical are now subtly off. It's not dramatic, but it's the kind of thing that cascades through every precision system on Earth simultaneously. The planet is not static. It's a spinning system, and everything we've built assumes it keeps spinning. 6 seconds is all it takes to find out how much we were counting on that. If you want to see what happens when we run the same thought experiment, but in reverse, what if Earth suddenly spun twice as fast? That video is right there. It's a different kind of chaos, and honestly, some of the effects are even weirder than this one.